Hello again, and welcome to NoCalc. In this episode, we will be discussing the intricacies of the exponential function and the number e. So, as we've already covered, the calculations for pi and for square roots is another natural number, which would be normal to calculate. Actually, this one is pretty easy to calculate using its Taylor series if we plug in 1. However, there's some things that I want to go over explaining e, which seem very confusing to me. In particular, there seems to me many different definitions of the number e. For instance, when I was first learning about the number, I learned it as the amount of money that you'd be able to earn using compound interest or continuous interest on $1 after one term with 100% interest. If we calculate this, this ends up being the value of the limit as n approaches infinity of 1 plus 1 over n to the n. However, there's many different definitions. For instance, I've also seen the common definition being the integral from 1 to e of 1 over x dx gives you 1, where e is the value which allows this integral to be true. Next, there's the Taylor series definition, where we take e equals 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. But finally, and probably the most known definition of e, is it's the base of the exponential, which allows the derivative of e to the x to equal e to the x. This one we're going to focus a lot on in this video, and in the next video we'll focus more on the other definitions of e and how they're all the same and compute the value. The main question here is, how do we even know that if a function is equal to its derivative, that it's going to be connected with an exponential function in the first place? For instance, why couldn't it be x to the power of e, or the sine of the square root of x squared plus 4, or something crazy like that? Well, the reason for this we'll be going over today. In order to explore e and determine which functions are equal to their derivative, we'll first start by defining f to be the set of differential functions equal to their derivative. Then, if f is a function that matches those properties and it has a positive value, we'll show that all greater values will also be positive. Then, we'll show that if one of the values is non-zero, f of x will never be 0. Using this, we'll show that for a non-zero function, all of the functions that are equal to the derivative must be constant multiples of that function. And then we'll finally use all this in order to show that any function that's equal to its derivative must be a multiple of an exponential function. First, we will look at the set f of all functions that are equal to their derivative. First off, let's pretend that we've never seen the function e to the x4. If we just take an arbitrary function f of x, which follows this, and let's say that f is the set of functions that are differentiable with f of x equals f prime of x for all x real numbers. It turns out that other than the 0 function, all other functions are never equal to 0. This is actually very important in allowing us to be able to prove that. Next, we will show that if f is a function equal to its derivative and it has a positive value, then all the following values are also positive. So let's say that a function is not equal to 0. So we have some value, a, for which f of a is not equal to 0. Now, first off, we're going to prove that if f of a is greater than 0, then it's going to f of x is always going to be greater than 0. To do this, let's suppose that there's a number b such that b is greater than a, with f of a equal to 0. And let's say that f of b is less than or equal to 0. Well, this means that there's got to be something that's equal to 0 between a and b by the intermediate value. Now, let's say that f of c1 is the first one that's equal to 0 after a. So, if we have this, we can use the mean value theorem on a and c1. We have f of c1 minus f of a over c1 minus a, being the slope between c1 and a. And this has to be equal to the derivative of some value c2. However, since c1 is less than ca, this is going to be a negative number. So, since f prime of c2 is equal to c2, f of c2, we have something else less than 0, and so we're going to be able to find c3 with f of c3 equals 0. However, this gives us a problem because c3 is less than c1, which is a contradiction to what we've said before. So, if f of a is greater than 0, then f of b is greater than 0. Next, we'll show that if a value of f is not 0, then the function is never 0 for any value of x. Now let's say that b is less than a. In order to account for this, let's think of another property of exponentials. We can multiply exponentials by adding the values that are inside. So let's take a look at, per se, x plus f of x plus a times f of negative x plus a. If these were exponential functions, this would end up being a constant. So we can take a derivative of this function, and hopefully it'll end up being 0. If we take the derivative of this, we end up getting f of x plus a times negative f prime of negative x plus a plus f prime of x plus a, f of negative x plus a. However, since all the derivatives are equal to their functions themselves, we're actually going to find that this all cancels to 0. So that means that we have f of x plus a times f of negative x plus a is some constant. Now, if we plug in 0, we would end up getting f of a times f of a. So we get that this is equal to f of a squared, which is going to be positive. Now, f of x plus a is greater than 0 for x greater than 0. So that means that f of negative x plus a must also be greater than 0. And so our function is always positive. Next, we'll show that if there is a function that is non-zero, that all of the other functions equal to their derivative are constant multiples of this function. Now let's figure out how we can use this. Let's say that our function exists that is non-zero. We know that all of these are going to be a constant multiple. So let's say that we have some other function, g of x, which is in our set f of all these functions. You will just remember g of x is equal to g prime of x. Then, let's take a look at g of x over f of x. We can try a similar trick as before and take its derivative, since we suppose that this is going to be a constant. So its derivative should be 0. And we can check, using the quotient rule, that this is g prime of x, f of x, minus g of x, f prime of x, over f of x squared, which ends up canceling because the primes don't actually change these functions. They're equal to their derivative, and so this is equal to 0. Which ends up proving that g of x over f of x is a constant, so f of x is equal to a constant times g of x, or g of x is equal to a constant times f of x. So our set f of all these functions must either be just the 0 function, or it can be written as c times some function, and it's a single function. Finally, we're going to show that if f of x exists, it must be an exponential function, and all other functions are multiple. So let's suppose further that this thing actually exists. In the next video, we'll be more rigorous in proving that it does. And let's take a look at why this must be an exponential. Now, since this is a constant times all the functions, we can pick a function, which we'll call f, such that f of 1 or f of 0 is equal to 1. And let's say that f of 1 has some value alpha. This is actually going to be, we'll prove that this is e later, but for now we'll assume that we don't know anything about e and we're going to prove it. So, let's take a look at the derivative of x plus a. Well, this is just going to be, or f of x plus a, sorry. This is just going to be using the chain rule, f prime of x plus a. So, f of x plus a is in our set of functions. So that means that f of x plus a is a constant times f of x. Furthermore, that means that f of x plus 1 is a constant times f of x. And if we plug in 0, we can see that that constant must be alpha. So, we'll use this function multiple times. We can see f of 0 equals 1, f of 1 equals alpha, f of 2 equals alpha squared, and so on. And f of n, where n is an integer, is going to be equal to alpha to the n. Now this is only for the integers, so we have to be a little more precise to get it for all the real numbers. Let's say that we have a value, we have to look at f of x plus 1 over something which we'll call n. Now this is going to be a constant times f of x. Now if we do the same repeating process, find that f of 0 equals 1, f of 1 over n is to c, and so on to f of 1 is c to the n. Now f of 1 over n must be positive, as we've shown before. So we find that c to the n equals alpha, so f of 1 over n is equal to alpha to the 1 over n. And then repeating this, plugging this back in with this idea, we get that f of m over n is equal to alpha to the m over n. So we have f of q is equal to alpha to the u for doing the rest. Finally, since our function is continuous, we can apply this to all the real numbers by squeezing in between the rationals, and we get that that is equal to alpha x. And therefore, we have proven that if we look at the set of functions that are equal to their derivative, if one exists, it must have the form of a constant times alpha x. And so we have some value for alpha, which is going to be the special exponential, which is equal to its own derivative. Now maybe it's 0, maybe it's not. We'll prove that in the next video. And we'll eventually prove that alpha fits all those definitions of e and calculate that it's about what it's going to be approximately. Thanks for watching, everybody.